please help me welcome Kyle and Yaron.
Thanks, Steve. I'm Yaron Friedman.
And I'm Kyle Scholz.
And we're here today to talk to you. We're here today to talk to you about high-performance search at Google. Kyle and myself are both members of the web search infrastructure team with specific focus on the front end of web search. And our job is, we don't focus on the back ends at all. Our job is to get the data to the user as fast as possible. Our day-to-day work has multiple facets, and the first of which is the A/B testing that's been talked about a bunch in this conference. We run tests tweaking the UI, tweaking the markup, and trying to make the page faster. We try to implement the best practices that have been talked about in the web performance industry, and we try to constantly improve upon the page. The second aspect of our job is to support developers at Google who are launching new features on web search. So obviously, we can't keep web search static. We need to continue to improve, make it better, make it more relevant. Our job is to ensure that the teams that are adding features to web search do it in a way that adds as minimal impact and overhead as possible, so it doesn't slow down the experience for our users. Before we go on, we welcome questions throughout the presentation. It's a bit bright, so it's hard to see you, but please raise your hand if you have a question, and we'll take it in flight.
Or shout.
So what we're going to do is we're going to talk about some of the key infrastructure features that we've implemented and used in Google Search over the past few years to make Google Search as fast as it is today. We want to talk about the things that we think have made the biggest difference. And we'll try to give a little bit of color to show how much of an impact they've had on Google Search. And after that, we'll set the groundworks to talk about the motivation for this latest latency reduction technique that we're employing, which is one of the many ways we're trying to make Google Search even faster still. So you guys are all at Velocity, so you're all aware that there are a number of best practices prescribed by the community. And that list is evolving and expanding, and that's great to see. We wanted to touch on a few of the small things that we think that need to be done because not doing it is a disservice to your user because you're essentially wasting bytes and sending extra bytes over the wire. So the first example is something that seems maybe a bit simple and not worth the time. But as Marissa mentioned in her keynote, when she mailed a code review off to change the page, Craig Silverstein pushed back on her and tried to say, hey, can we do this with less bytes? And that's a day-to-day thing at Google. We've never lost sight of this, and we've written tools to help. But the reality is that there are a lot of tags in HTML that aren't necessary. They're implicitly done by the browser, and they don't add value. So why waste the bytes on them? Similarly, why include HTML comments or JavaScript comments in your JavaScript and serve those bytes to your users? You may as well use server-side scripting server-side comments to avoid having to send those bytes, and you get the same result and the same readable code for your developers. Another key element is minifying your JavaScript. If you've looked at the JavaScript on Google.com, it's not very readable. Kyle will talk about that in a little bit, about our goals there. Crush images it was talked about a lot last year. And this is just, the idea is that why would you send more bytes than you need to convey the same rich experience? And so there's a lot of tools around that, and it's nice to see. You can easily run a single command line and crush your images. It's actually kind of convenient for us to do this because we use any change list that I receive that's trying to modify the search result page. I code review through a web tool that we have. And so I can use PageSpeed or one of these other tools right there and see that this image is as minimal as possible. And it's really nice to be able to do that almost automatically as part of the process. Gzipping is important, obviously, and Tony Gentilcore will talk about how you can maximize that. Another key issue I want to talk about is that it seems like it's all too common to send catch-all JavaScript that works for all browsers everywhere. And it doesn't seem, and we believe that that's the wrong approach. We believe that it's important to use server-side detection of you can look at the user agent, and at the server side, you can determine what bytes to ship. And we do that if you look at our JavaScript. We will ship tailored JavaScript to IE or Firefox or whichever browser, depending on the user agent. Anyway, that's just a subset of minimal things that we think you need to do. And it's great to see page speed came out last month, or this month, and there's all these other tools that have been talked about at the conference. And we put up page speed here because I'm particularly fond of it because it has a nice explanation around each of the rules. It doesn't just arbitrarily tell you, do this, and not give an explanation why. It's sort of a one-stop shop. But of course, as long as you're using any of these tools, we think you're much better off.
So we're going to dive into optimizations a little bit. And you'll notice the first one here, HTTP chunking. I'm at least the third person at this conference to talk about. It's something we've done for a long time at Google and has serious, significant advantages that I think you've heard a little bit about. But we're telling a story here, and I think our angle will help sell us a little further. So in short, searches are really fast, but they're not free. In this example query here, it took 0.25 seconds for Google to perform the actual search. It would take the same 0.25 seconds whether I'm accessing this page via a modem or fiber. This is the time that it takes Google backends to actually do the real work in search. It's also true that about 25% of one of our response pages can be delivered without doing this part, without talking to Google backends. So with some optimization and using HTTP chunking, we want to take advantage of this. This 25% of the page includes things like the universal navigation bar, the search form, and more importantly, stuff that you can't see. This is JavaScript and CSS that's necessary to render the page. Chunking is actually really straightforward. Where in a traditional response, you have a content length header that indicates the size of the body portion of your HTTP response. And it's implicit that you know the entire size of your document before delivering even the header in this case, because you need to include it first. In the chunked transfer world, we instead include a transfer encoding chunked header, and then we can respond with an arbitrary number of chunks where we only need to know the size of each chunk before outputting. And it offers a huge advantage. In this chart, the dashed vertical line indicates the time at which a backend response is available. And you'll see that in the chunked world, when we can begin delivering content earlier, we enjoy a significant advantage. We get the full impact of, we're able to use the entire 250 milliseconds that our backends are performing search in this case. For our dial-up users, and our cable users enjoy a considerable advantage as well. So you're seeing a 10% across the board improvement regardless of users' connection speeds. The other big thing that I think Marissa pointed out this morning is that when we do this, and I'm going to jump back a slide or two, we deliver some of the experience to the user. The search form updates, we deliver all of the content possible so that the browser and the user have something to work on while we're catching up. Chunking is generally applicable anytime you do expensive work to produce part of a response. And I specifically mean that there's some other part of the response that you may be able to deliver while you're doing this work. It isn't ideal for all applications. If you're using e-tags and you're getting a great advantage of them, they're just not compatible. E-tags work by responding with a 304 not modified. Anytime the e-tag provided on the request matches the response that you're about to deliver, which implies that you need to know what your response looks like before you start sending anything over the network. The other potential issue is that if you use chunking excessively and you're flushing your buffer a lot, you may introduce excess packets, and every new packet that you add to the stream is another opportunity for a TCP retransmit, and that is the worst possible case for network latency.
So the next optimization we want to talk about is minimizing connections. I think Marissa said it well this morning when she said that there's a small image costs you a second or $1, a large image costs you $1.01. And that's generally what we've found, that anyway, the single best way to reduce user perceived latency is to minimize connections. The almost obvious application of this technique is with CSS spriting, to sprite an image. There are still lots of websites out here that, although they use it to some extent, they still provide some images that are not part of their sprite. Steve and I actually argued about this a little bit last week, about whether or not this was a common technique used on the web. And I think it is a common technique, but I don't think it's used enough. The benefit that you gain by putting all those resources on a single connection is immense. And one other advantage is that when you're used to pulling out parts of this image, you can construct more interesting UIs without incurring additional connections. And what I mean by this is if you think of a review site where you have different ratings for different videos or what have you, you may have a 3-star rating, a 4-star rating, and if you treat those as separate image requests, you're going to really incur a lot of additional latency that's not necessary. Whereas if you're used to picking out little stars from a composite sprite, you can deliver that rich experience without the additional connections. And there's a big savings there. How big a savings? Well, there are 2 recent additions to Google Search that I want to talk about. There's the Search Options panel, which is on the left-hand side and provides additional search customizations and refinements. And there's also Google Search Wiki, which allows you to promote, demote, and modify your results. Through experimentation, these teams came to us and they talked about the assets they wanted to use to decorate their page, to make it a richer experience, and to make it more engaging for users. For both of these projects, we experimented with a supplementary sprite that would provide all of their content. So we don't need to worry about affecting our mainline users with additional data that they don't need. And they can iterate quickly on their experiment. But what we found through experimentation is that both of these experiments suffered from additional latency from their sprite, even when their sprite was only a few hundred bytes. And the picture, which to me is the most glaring reason why this is important, is that it could cost us as much as 10% in page load time to download these sprites. And that really would affect our metrics and affect the perception of our page. So that's something we wanted to avoid. If I can jump back for a second, you'll remember, if you were at the keynote, you'll know that Marissa talked about the sprite the image request for the shopping cart for the Google Checkout, for Google Checkout ads, and how we optimized that to use a table to render that shopping cart. Well, we wanted to make that feature more pronounced, so we ended up changing to Google Checkout button. And even though that's not used on every page, it's still, in the end, it's better for us to include that as part of the large one-time download of the sprite, which is highly cacheable, than to introduce a separate request.
So I'm going to talk a little bit about optimizing script usage. A lot of you are probably familiar with minification tools for JavaScript. These strip out your white space and comments and also obfuscate code for the purpose of minifying. These tools are spectacular and can reduce the size of your script by more than half. If you're not using them, you're doing yourself a disservice. The other useful technique is to bundle your scripts. Yaron's already pointed out the value of optimizing for connections. If we had a case where adding one connection cost us 10% in terms of load time, clearly there's an advantage to delivering all of our external JavaScript in as few connections as possible, which should be one. So while it's a great idea to bundle your JavaScript, there is one caveat. If you have a number of modules that may be maintained by different groups, you need to keep in mind that the bundle is now atomic, and there's a high cost for every download. It should be treated as an atomic unit and put on a release schedule, and sometimes this is a little bit demanding for teams. So just keep in mind that there's a high cost to moving to a single atomic bundle. The other technique that's really effective is deferring JavaScript. We use this in Google all over the place, really. The bulk of our JavaScript is delivered as one deferred bundle. Our approach to this is to identify all of the JavaScript that isn't required to render the page. This is generally JavaScript that's triggered on user actions or add-on load time. A good example is the JavaScript that supports the finance menu box. If I do a search for Apple, somewhere embedded in the Apple corporate website result is a link to the finance ticker for Apple. And there's a little plus icon. And if I click on that, some action's going to happen that updates the page and downloads a finance chart and shows you the current stock quote. Since it's not necessary to have that information at initial page render time and we require a user action, we can defer that to much later in the rendering, much later in the page lifecycle. So we bundle all of this functionality into one place, and we load it at what we call the effective document complete time. This is before onload, but late on the page, and I'll show you how in a minute. It's also important that here, sometimes the user may be able to interact with the page before the JavaScript is available. Since we're doing some rendering, well, we hope we're doing some rendering before we even request the JavaScript, very fast users may begin to interact with components that have JavaScript-triggered functionality. So we need to do something smart. And going back to my finance my finance many box example, if a user were to click on the plus icon 7 times, chances are we really only need to acknowledge the first such event. But if a user enters a series of keystrokes into the search box, it's important that we catch up with them when we're dealing with our suggest feature, which suggests queries. So when loading JavaScript, we use a variant of Steve Souders' script DOM element. And this is a method of script injection that tends not to affect latency measures, such as page load time. It's important that when you use these techniques, you don't inject script tags into the head tag, because some versions of Internet Explorer will lose the state of persisted form elements and iframe history anytime you inject something above them in a document. So it's also important that you put those components that you care most about persisting as high on the page as possible and never, ever inject anything above them, whether it's in the head or the body. So instead, you should inject script elements into a DOM element that has already been closed and is somewhere within the body in order to avoid an operation aborted exception.
So Google search is pretty fast, but that's not good enough. As I mentioned before, we have developers that are constantly finding ways to make the search result page a richer experience and better for our users. And we want them to, and we need to support that. Google can't just stand on its feet. So in order for them to have room to add these features, which are necessarily going to add bytes, we need to constantly look for ways to make search faster. Also, just if we can make today's server faster with today's features, we believe that will be a win for us. So let's recap. What have we done? With the micro-optimizations at the beginning, we've ensured that we're not serving more bytes than we need to give the UI that we're providing to our users. We've leveraged HTTP chunking to deliver content to the user while we're doing the back-end work. And one nice thing also about this is that our sprite appears in that header chunk. So actually, the browser can start downloading those static assets while in the parallel with us generating the search results. And that really gives the browser a head start at rendering the page. We've realized that minimizing connections is vitally important, so we sprite what we can, we bundle the JavaScript, and we deliver that JavaScript late, or as late as possible. So if you look at, we have this JavaScript and these images that we've externalized, and we've made them highly cacheable. We've tweaked the caching headers to make them, to try to get as high a cache hit rate as possible. And that's done a good job of moving some bytes off the page for every request. So if we're trying to make the page faster, one thing we could look to do is to extract more content and identify more content for caching and extract that as a separate resource. But we believe that there's no naive way to do that for Google search, at least. Because if we try to extract any more bytes, we're going to put another network connection on the critical path to rendering the page. And so for users with a cold cache, we're going to slow them down. So it's important that if we're going to do any kind of effort to pull bytes out of the page and to make the page faster, we have to be smart about it, and we can't just cache something like the style sheet, for example, because we need the style sheet to render the page and to specify the nav logos to get that image downloading quickly. So let's take a step back and let's look at what makes up a Google search result page. So I opened up a search result page in Firefox, and I looked at Firebug, and I looked at the various parts of the page, and I think you'll see there's some interesting things. First of all, the page is comprised of 3 primary connections. There's the result page, there's the image, there's the sprite that we talked about, and there's the external scripts. Because of our caching headers, we've achieved a 90% cache hit rate on the images and the JavaScript, so we don't think that there's much room to optimize there. So we need to look elsewhere to make the page faster. So let's look at the actual HTML document that comprises the search result page. Now keep in mind, we can't cache this because we need to ensure that we have accurate accounting of searches and ads for a variety of reasons. One is to be fair to our advertisers so that they're properly being billed for their ads and they're getting the accurate accounting of their ads being displayed. But also because we have engineers working on improving the quality of the page in terms of improving ad quality and search quality. And so they need to know if these searches and ads are getting clicked so that they can do accurate analysis of the page, accurate analysis of the ranking algorithms and continue to tweak and improve them. Okay, so we can't cache the HTML page, but what comprises an HTML page? So there's a small chunk of JavaScript, which works out to about 8% of this sample page, which is the scaffolding. It's needed to lazy load the JavaScript and to do some infrastructure for the page. There's also the style sheet, which I mentioned we don't want to externalize, which is 12% of the document. So that leaves the remaining 80% of the page, which is HTML with maybe some inlined styles where we think it's appropriate to inline them as opposed to declare them at the top of the page in the style sheet. Of that 80%, 60%, so of the total page, 60% is results and ads, and the remaining 20% is static HTML that's sort of just scaffolding for the page and doesn't depend on the user's query. So if we look at the inline scripts, the CSS, and that static HTML, we can identify 40% of the page which doesn't really depend on the user's query. And so we call this the static Chrome. There's the remaining 60%, which is the dynamic data, and we don't think that there's much we can gain here because that's the actual result in ads, and we can't cache it. And it's important that we don't naively add additional connections to make use of this, to recycle or benefit from this static, from realizing that there's the static Chrome. So here's our challenge. We want to make search latency faster by cutting out a lot of bytes that are unnecessary. So we've identified that there's the static part of the page and the dynamic part of the page. And we're going to try to find a way where we can recycle the static part of the page from one query to the next and only deliver the dynamic part for each user query. But there are some constraints for web search and that we need to go over before we get into any kind of solution because this might eliminate the possibility of some solutions. So one such constraint is that we need to preserve the pace of innovation for our developers. A stagnant Google is bad for us and it's bad for our users. So what we can't do is create a parallel development track for developers to create features in, one which is a faster experience and one is a regular experience. We need to support the existing developer model. We also can't, in the long term, provide a different experience to different browsers. It's not acceptable. We don't preferentially pick a browser in which you enforce it upon our users for Google search. As I talked about, we can't just naively cache results and ads because we need to maintain an accurate accounting of that data. And finally, Google search is a pretty light and streamlined experience. It doesn't have the feel or the connotation of a heavyweight and complicated AJAX application. And we don't want to introduce that. It's important to us that Google remains a fast and easy to use web page.
Yaron brought up the part where I like to point out, does everybody here know that Google.com still works in Netscape 4? Do any of you have websites that work in Netscape 4? Netscape.com doesn't work in Netscape 4, so anyway, supporting old browsers is actually really important to us, and there are a lot of places in the world where people are accessing Google where the equipment and the software is a little behind the times. So it's been critical that we continue to provide them a workable search experience, and we like to keep the feature set as close in parity as possible. Anyway, so we're talking about this new thing we're going to build, and we're calling it soft transitions. The idea here is that there's a single stable window for all of your searches. We call this a search player. Clearly, we're starting to talk about a web application for search. The idea is that rather than communicating in complete documents like we do today, we're going to communicate in fragments. Those fragments that are the same from one query to the next, we want to recycle to the best of our ability. Also, as Yaron pointed out, we don't want to reinvent all of our search features, so we want to find a way to hook seamlessly into the existing experience. You've probably deduced that this is rather Ajax-y, and we're going to need to do some things to support regular old browser behavior, bookmarking, back and forward, refreshes, fun and simple things like that. Also, since we're doing something with, since we're managing page fragments, and we're trying to manage multiple searches in one window, we need to persist the static and dynamic fragments that make up a search page and be able to replay them appropriately as users navigate among queries and to and from search result pages. So how does this work? We have JavaScript that binds some special handlers to all of the search controls on a page. These are forms, these are refinement links, and other page features. And instead of letting these things behave as normal, we direct them through some alternative transport. And so far in our conversation, this may be to an external script block that might retrieve JSON. This could be an XML HTTP request, or it could be an iframe. The responses look almost identical to what we produce today, except that they're aided by a little bit of JavaScript that is capable of popping content over from this alternative transport and into the host page, this single stable page that is our search player. And that was an animated pop. So I mentioned that we need some alternative transport to do this. It's not possible to transmit just document fragments using traditional browser interaction models. So we're going to need to use something else. We selected iframes because, at least at its maturity level, it's the only one of these transports available that enables progressive rendering. And progressive rendering is a key piece of, I guess, of our latency universe. HTTP chunking is effectively step one in progressive rendering, where we want to show something to the user as soon as possible. But also when users are on slower connections and there's an opportunity for the browser to paint the current state, when it doesn't have all of the bytes, it's important that we're able to do so. So iframes enable us to use the DOM parsing model and rendering that are currently afforded us by all browsers to achieve progressive rendering when we're doing something that's a little bit more like Ajax. I will point out that XML HTTP request offers this in some browsers by offering intermediate access to response data, but this isn't universally supported yet, so it wasn't an option. When we talk about recycling, we're really talking about doing caching, but a little bit differently. We're caching content. So far, we've talked about caching content for a session where we have static and dynamic fragments that we're managing inside the player. We deal with this part by delivering what we call the Chrome. And I don't know if you've picked up on, this is an alternate use of the word Chrome for Google. We're overloading terminology a little bit, but I think we used the word Chrome first. In any event, we detect when a user is making their first query or when they don't yet have a version of Chrome available. And we'll deliver it with the first response. Also, we have another mechanism for caching where we're able to disk cache Chrome using a prefetch that happens during idle time on the home page. The implications of the first method are that every time we build a results document, we generate new Chrome. We generate a page very similar to what you see when you visit a traditional search results page. But we determine whether we're going to send the static portions of that back based on something the user tells us. The user gives us a signature that we pass back and forth that indicates the version of the Chrome that they're using. That signature is actually, it's a fingerprint of the Chrome, which enables us to seamlessly recognize changes in the Chrome that may be made by anybody. There are a number of people that work on search features, and they could check in a change at any time that may have some impact on our Chrome. And we can adapt to that change immediately without doing any type of manual versioning. The other part of this is just the classic web application problem where we need to reinvent history in bookmarking. This should look pretty simple. We support bookmarking by storing search state in the fragment identifier. So you'll see when you're using this infrastructure, your URLs are www.google.com/hash, some big string of URL parameters. So this enables us to support bookmarking and links and other sharing features. Also, to support back and forward and refresh behavior, we use fragment polling. This means there's a timer that's always watching the state of location hash in Firefox, because that's the only dependable way to do it. And in IE, we actually let the iframe that we're using for doing all of our communication indicate the current state of the application. In the future, web browsers are going to do better things about this. On-hash change is a step in the right direction, but there are bigger, better things that I'll talk about in just a moment. But first, is this all worth it? We're doing something kind of big and crazy here, moving away from a model where search doesn't have a lot of JavaScript involved in the basic infrastructure. So clearly there has to be some significant advantage for us to pursue this any further. And you'll see, we're going back to my chart from earlier in the presentation, where now on top we have a traditional chunked search response that is about 12K. And backend response time is, again, hypothetically 250 milliseconds. At dial-up speed, being able to recycle to Chrome enables us to remove so many bytes from every response that we're able to save almost 500 milliseconds for these users. This is really offering us a big advantage. But you'll note that this is primarily a byte savings optimization, so it doesn't offer us as big an advantage for users that are at the top end of the throughput curve. So I'll stress that this here is just a first step. We've been forced to hack around a lot of existing limitations in browsers and quirky behavior. But we're looking forward to the next thing, and this has given us an opportunity to identify the features that we're going to need out of the next generation of browsers. And HTML5 has already done an excellent job of specifying the set of features that we need to make better web applications and even make a better search experience. The first one I mentioned, currently HTML5 doesn't support access to intermediate data in some browsers. It's indicated in HTML5 that this is a requirement. It'll be great when that happens. XML HTTP request is far more versatile than using an iframe for communication, just because of the callback structure that it affords. It's possible to associate every action with a callback, where when you're working with a single iframe, you need to manage a lot of state yourself. The other much bigger piece is the new history infrastructure or specification in HTML5. The most exciting part of it for me is history push state, which for the first time gives web application developers complete control over the history stack from their web application's perspective. A couple of its great features are that anytime you push onto the history stack, you can provide a set of custom data that will be passed to a callback function anytime back, forward, or refresh are done. And the biggest feature for me is it enables you to update the canonical URL, a real URL, for your application state, where presently there is no way in any browser that I know of to change the actual URL of a live application without destroying and creating a new window context. So this is really big. It has huge implications for bookmarking and sharing. Now we'll have real URLs that we can share that don't have fragment IDs, and any way you access these things are always going to work the same way for all users. It enables graceful degradation, where you may offer a web application to users with modern browsers, but gives something else a little bit more primitive to your older users. Now you can use the same URL scheme to communicate with them and choose whether you're going to show your web application on the fly. Where currently a lot of web applications must download some infrastructure, check out anything that might be in the fragment ID, and issue a subsequent request serially. Now you'll be able to do all of that stuff at once because everything about the application state is encoded in a real URL. Bigger yet, if these aren't too many things. It enables you to convey information in the HTTP refer where currently if you're managing all of your application state in the fragment ID, that information just isn't made available to third parties. And it gives you real control over the HTTP referrer as well. So if there's private information that you want to hide, more information that you want to expose, you have complete control over that. And finally, it makes your web application much more amenable to crawling, which is something I think people are going to start caring about soon enough. As web applications become more mature, we're going to want search engines to understand them. So we're very eager for browser developers to get on this stuff, and those are our top priorities for them. Something I guess we haven't mentioned is some of you are already using this experience, and you may not know it. So Yaron's going to demo it and give you some clues.
So if I load up, we actually pushed this out a few months ago to a subset of users. So if I'm on the google.com homepage and I do a search, I don't know if you can see it on the monitor, but you'll notice that there's a fragment in there. And what we've done is we've only delivered the dynamic parts of the page. If you look at the search response, this one weighs in at 10K, which is less than it would be otherwise. This is flowers, I guess, is sort of a heavy query. There's a lot of features on the page. I can try something else. This query is as little as 4K. So you can imagine that gives us a number of advantages. And so we're just recycling the static parts of the page throughout. If I go back to the home page, you'll see I didn't download the JavaScript, and I didn't download the logo. I didn't download the Chrome, because those have all been disk cached, and I can search, and it'll reuse that part. So this has a great benefit from one visit to Google to another when you're searching from the home page. That's our demo, and thank you.
Thanks, guys. Okay, Steve says we have time for some questions if anybody has them. We might, oh, I do see one. Oh. I can barely see one in front. We should find a way to share that information a little better. Yes, specifically, if you're relying on form persistence to manage any part of your page state, so when people go away and come back, you have some of your application state persisted in an HTML form. That information can get wiped out if you inject a DOM element anywhere above that, the form element containing that data. And I believe this is at least an IE6 issue. I don't know if it's.
I think it's IE7 as well.
Okay. Offhand, I don't have a link, of course. But if you want to find us afterward, we can probably dig it up.
Yeah, we have a little test page that shows it.
Anybody else? All right. Thank you.
Thanks.